The amazing fact is that carbon has the ability to form more kinds of shapes than anything else. And this is based upon its structure that when it chains up in molecules, it can form bonds in as many as 4 different directions at once. The bonds can be single bonds, double bonds, triple bonds. The bonds can rotate. It's very, very versatile. And I gave many examples of that versatility beforehand. So what we're going to talk about is the fact that carbon's versatility gives it an ability to make more different kinds of substances. It can bond in more ways with more substances than any other common element in the universe. In fact, the surprising truth is, if you took all the elements in the periodic table that naturally occur on Earth, besides carbon, and you compared them with carbon's ability to form molecules, you would discover that carbon by itself can form the basis of more compounds than all the other elements put together. These right here that you see on the slide, these are not the names of molecules. These are the names of classes of molecules. Most of these have hundreds or thousands. There are thousands of different alcohols that have been described. There are many, many hundreds and hundreds of carboxylic acids have been described. There are many different sugars. So carbon is just really spectacular in this regard. And so the largest branch of chemistry is called organic chemistry, the chemistry of things based upon carbon. Okay, this field is essential to many fields of study. If you're going to be a nurse, a doctor, somebody in the healthcare field, you will not only have regular chemistry, and you will not only have organic chemistry, you'll have a whole specialized field of called biochemistry, which is like the aspects of chemistry that's a part of medicine, that's a part of food production. I mean, there are a lot of jobs here, right? People don't realize just how many different jobs or different degrees require people to have not just 1 year of chemistry, but multiple years of chemistry. So this is one of the reasons why. You need a lot of advanced knowledge of chemistry to do medicine or to be involved at a high level in the production of food. Chemistry is actually how we figured out how information is carried through living things. We all recognize the DNA molecule and its single-stranded cousin RNA. There's nucleic acids. We've learned in biology how that's used to, copy and transmit and express information in living things. Well, this is a branch of biology. It's called molecular biology. And to do molecular biology, man, do you need a lot of chemistry, right? So, like if you're in law enforcement and doing DNA for forensic science, crime scene investigations, you probably have a couple years of chemistry. And this is very practical. The world relies very heavily on carbon-based chemistry. Almost all plastics are based upon carbon. In fact, the building blocks of plastics like PVC or polyethylene or styrofoam, the building blocks of plastics we actually get as byproducts from harvesting petroleum and natural gas. Fossil fuels are basically based on carbon. And so the people who work in the fossil fuel industry to power our economies, they have a lot of chemistry. If you're a geologist who's working in fossil fuels, you're also a geochemist, right? Now, fossil fuels do have a downside, and the downside is that while they are pretty cheap, which is one of the reasons, and they're so popular, it's because they're very cheap. But they do pollute the atmosphere, and they do contribute to global warming. So there's a downside, but nevertheless, they are still very important to our global economy. And they contain the simplest type of organic molecules. The simplest type are called hydrocarbons. Can you guess which 2 elements are involved in hydrocarbons by their name? I'm sure you can. And it's just those 2. And the normal structure is that you've got a chain of carbons, and they're all surrounded by hydrogens. Now, it's an interesting fact that when you're talking about hydrocarbons, these particular organic molecules, they won't dissolve in water. They just won't. And the reason is that the hydrogens surround the chain, and they don't give any place for water to get in there to dissolve it. And so these molecules, because they won't dissolve in water, they're said to be nonpolar. Here is a vivid, colorful illustration of that. We've all seen gasoline or oil that gets on the roadways, and when the roadways get wet, we actually see it shine. We often see a rainbow display of colors. Well, why are we seeing that? Well, it's because the oil and gasoline doesn't want to mix with the water. And so it lies on top of the water as a separate layer, and the separate layers reflect light differently. And as the light moves through one layer of one liquid to another liquid, it actually gets bent. And as it gets bent, we see different size waves of light. And our eyeballs interpret those different size waves of light as color. So that's what you're seeing here. The fact you see color on an oil slick on a wet day in the street is evidence that they are nonpolar, that they will not dissolve in water. Now, hydrocarbons form straight chains, branching chains, and cyclic structures. By themselves, hydrocarbons only have a limited number of shapes, but it's worth understanding what we mean by that. So if we talk about butane, which is a 4-carbon chain, it has a formula, C4H10. That means there's 4 carbons and 10 hydrogens. You can see from the structural formula what that looks like. You see the 4 carbons and the 10 hydrogens arranged around that. We can also model that as a ball and stick model. This is what we mean by a straight chain. The chain of carbons is imagined as being effectively straight, going in the same direction over and over again. But if we take these same 4 carbons and 10 hydrogens and slightly rearrange them, it will still be C4H10, but we will have a different shape. Now take a look at that. This is sometimes called isobutane. It has a different shape because it's not a straight chain, it's a branching chain. Finally, we can take a chain, we can completely bend it around in a circle to make a ring. We call those cyclic structures. This is cyclobutane. And again, you see the structural formula and you see the ball stick. These are the basic shapes you can make with hydrocarbons. So by themselves, they don't have a huge amount of shapes, but they still have some versatility on their own. When we try to name these things, we have to keep cognizant of how long the chains are, and we also have to keep track of what kind of bonds they're. If the hydrocarbon chains only have single bonds, they are said to be alkanes. Alkanes. When we look at them, when we look at the pictures, this is the first 6 common alkanes. You'll notice that they all have the same general form. Since they're all alkanes, we use the suffix ane, ane, to name them. Methane, ethane, propane, they all have that ending ane, and that means that they're alkanes. Why do they have that ending? Because they only consist of single bonds. Only single bonds. Now, if it's only single bonds, that means that each carbon in the chain is connected to as many atoms as possible. Each carbon in the chain is really hooked up as much as possible to other atoms. And so we say it is saturated. So let's explain what we mean by that. Here's ethane. How do I know it's ethane? Because monkeys eat peanut butter. I'm going to say that again. Monkeys eat peanut butter. That means methane, ethane, propane, butane. I have 2 carbons, so monkeys eat. Eat sounds like ethane. This is ethane. And the key thing is that every carbon, both these carbons, are completely saturated. Let's count. 1, 2, 3, 4. So this carbon has 4 things it's hooked to. And how about this carbon? 1, 2, 3, 4. Also complete. So it's all single bonds, and each carbon in the chain is said to be saturated. Now, if you start having double bonds or triple bonds, that means that the carbon atoms in the chain won't be saturated because they won't be hooked to four other atoms. In which case we have to keep track of that, and we have to name them differently. If one of the carbons in the chain has a double or triple bond, that chain is said to be unsaturated. Look down here, we're going to take ethane. We have a single bond between the 2 carbons. Now we're going to replace that with a double bond. And you know what? That means it can't connect to 2 of the hydrogens. It has to get rid of those. We now say that this is unsaturated because the double bond, and we don't call it ethane. Ethane was only for single bonds. So since it now has a double bond, we have a different suffix. Double bonds are called alkenes instead of alkanes. All right, single bond alkane, double bond alkene. And if you have a triple bond, which is possible with carbon, you have a triple bond, well, we use the suffix YNES, which is pronounced ines. Triple bonds are called alkynes. So alkanes, 1, alkenes, 2, alkynes, 3. Alkanes, alkenes, alkynes. Now, this is starting to get rule heavy. You're noticing we're adding rules and it's getting complicated to describe them. Well, that's kind of the nature of the beast. And the reason why we have to have all these rules is because, again, organic chemistry is the biggest branch of chemistry. There are more than 100,000 described compounds based upon carbon. So you just have to have a bunch of special rules to keep track of it all. Now, when the compounds are relatively simple, like hydrocarbons, you don't need that many rules. When you start adding functional groups and the molecules become bigger and more complicated, well, then you need more rules. These rules are not built into nature. They're not etched in stone. We didn't discover them in experiment. They're just rules that we made up because they seem useful. We call them conventions. There's different conventions for naming and drawing and modeling carbon-based molecules. And this is 3 different models, 3 different drawings for the same thing. Right here you have a skeletal formula. Just got the outline of the structure, it's flat and 2-dimensional. Here you have a ball and stick model. It's kind of 3-dimensional, but it makes it look like all the atoms are the same size. And then you have a space-filling model, which is getting closer to the actual shape. All of these are attempts to draw or model 5-alpha dihydroprogesterone, which happens to be a steroid hormone that all of us use in our bodies. By the time you start getting to things like this that are really complicated, the IUPAC rules become very complicated. Now, for us, the most complicated thing is not drawing. No one's going to be expected to make a 3-dimensional drawing of an organic molecule. That's not fair. We don't really think that that's good sport. But we do have naming rules, or what we call nomenclature. So the nomenclature, it is important that we do follow it, even at the lowest levels. Every chemist in the world uses the same set of rules. They're called the IUPAC rules. IUPAC means International Union of Pure and Applied Chemistry. And again, for the simple things we're looking at, we don't need a huge number of rules, but the rules become quite complicated as we go deeper and deeper into this topic. Okay, so what are the rules based on? The rules are going to be based on how long the chain is, what kind of bonds are in the chain, and what kind of functional groups are attached to the chain. So here we have a picture. This is a structural formula, complete structural formula. It shows all the atoms and it shows all the bonds. Most of them are single bonds, but you see right here, there's a triple bond. And so the question is, how do we name it? That's how we use the rules. We use the rules to explain how we're going to name the thing. That's what we do. And our first thing we're going to want to find out is we're going to want to find out what's the longest chain. Now, when we specify the chain, and you will find this in your organic compound study guide, there's a table on the first page, and for the number of carbons, for the first 10 carbons, it tells you what the prefixes is. Now, I keep saying monkeys eat peanut butter because I have a hard time remembering meth, eth, prop, and bute. Those words don't sound like numbers to me. So I go monkeys eat peanut butter. That helps me remember I'm talking about methane, ethane, propane, and butane. But the other ones, curiously, are more familiar because we use versions of these prefixes in math. A 5-sided polygon is a pentagon, and a creature in the ocean with 8 arms is an octopus. And so these things, pent, hep, heps, oct, non, dec, those are more familiar to us. And so it's not as hard to remember. But meth, eth, prop, bute, monkeys eat peanut butter. It's a good memory aid, very helpful. You might look at this and say, what's the longest chain? Well, you can't count all of them. You can't just go 1, 2, 3, 4, 5, 6, 7, 8. That's not correct. You have to say which one of these is the main chain. The main chain has to be the longest chain. So we can start here. We could go up and down, vertical. 1, 2, 3, 4. Okay, so there are 4 carbons in this chain, but that's not the longest chain. Or we could go 1, 2, 3, 4, 5. 5 carbons in this chain. Well, that's true. We could also go 1, 2, 3, 4, 5, and there's 5 carbons there. That's true. But none of those is the longest chain. The longest chain is 1, 2, 3, 4, 5, 6. That's the longest chain. Since the longest chain is 6 carbons long, it'd be kind of a hexane. The prefix would be hex. How do we count it, though? Because it's no good for me to say, oh, it's 6 carbons long, but then I don't know which carbon is which in the chain. I have to be able to specify where it is in the chain because I still have to explain this triple bond, and I have to explain these things that are not part of the main chain at all. You know, I have to include them as part of the name. That's why we have to follow the rules, because the names actually describe the structure. We want to make sure that we have a consistent way of doing it. Okay, so what to do? Well, let's identify that chain. 6 carbons long. And again, it's this particular order. And if this was all single bonds, this would only be a hexane. A hexane. Hex is a prefix that means 6. Ane means it's all single bonds. But of course, we got a triple bond. And the question is, where does the triple bond occur? If we go this way, 1, 2, 3, 4, we get the triple bond on the 4th carbon. So that's one way. Or if we started backwards, if we wanted to go backwards, it'd be 1, 2, and the triple bond would be on the 4th carbon. Well, you might think, well, I'm an English reader. I prefer to go left to right, so let's do it that way. But in actuality, these are flat 2-dimensional drawings of 3-dimensional things.
This fact that the molecules actually have 3-dimensional shapes might seem obvious, but we really need to think about it carefully. Here, I've created an animation showing the rotation of a hydrocarbon chain. In fact, it's a hexane with the triple bond on the 2nd carbon in the chain. When we draw a hydrocarbon, we usually draw it in a flat 2-dimensional way, but we have to be able to use our imagination sometimes to see what it might look like from a different perspective in order to name it correctly.
And so it actually doesn't matter whether we number them left to right or right to left. All that matters is, can we find the longest chain? So it turns out that since going this way puts the triple bond on the 4th, and this one puts it on the 2nd, yeah, we prefer the 2nd. So we're going to go 1, 2, 3, 4, 5, and 6. That's the way we're going to do it, because that is the most logical solution, to have the triple bond, that is, on the lowest numbered carbon. Because the chains can become very long. It makes more sense to start with the lowest numbered carbon. Now, what do we do with these things that aren't part of the main chain? Well, we notice that both of them are attached to carbon number 4. We can now see that that's carbon number 4. And if we look at this CH, we see this is very similar to the structure of methane, which is the simplest carbon. So when you have the building blocks of methane sticking off the main chain, we say that's a functional group, and we give that functional group a name. We call it a methyl group. The triple bond means that this is not going to be a hexane, it's going to be a hexine. And the 2 methyl groups, here highlighted in orange, are both coming off the 4th carbon. So we're getting ready to name it now. We now have all the information we need to name it. We see that it is a carbon chain that's 6 carbons long, so the prefix is hex. We know that there's a triple bond appearing on carbon 2, so instead of being hexane, it's going to be hexine. And since we have 2 methyl groups attached to the 4th carbon, our name's going to have to tell us that. It's going to have to tell us that we have 2 methyl groups attached to the 4th carbon. And so this is the solution. 4,4-dimethyl 2-hexine. This is the 6 carbon chain that has a triple bond on the 2nd carbon and 2 methyl groups attached to the 4th carbon. I'm just going to say that again. This is the 6 carbon chain that has a triple bond on the 2nd carbon and 2 methyl groups attached to the 4th carbon. Okay, so its name is 4,4-dimethyl 2-hexine, and that's the logic of it. Now, when we're drawing these things, we're drawing the hydrocarbons, we have different formulas. The molecular formula, you're going to be happy to know, is something that you already know something about. You already know all about molecular formulas. How do I know that? Because if you've ever said or written H2O instead of water, or wrote down CO2 instead of carbon dioxide, you're using a molecular formula. Here we see that ethane's molecular formula is C2H6. What does that mean? There's 2 carbons and 6 hydrogens. We see that propane's molecular formula is C3H8. What does that mean? 3 carbons and 8 hydrogens. That's what it means. That's all that it means. That's all that it tells you. That's a molecular formula. Well, for a lot of times, that's all we need. But in organic chemistry, in case you haven't figured it out, shape matters. That's why this presentation was called The Shape of Life. Shape really matters. And so the structural formula tells us something about the shape, because what the structural formula does for the same substances is it shows the position of all the atoms, and it shows the location and the type of all of their bonds. It shows all of them. So you can see now that ethane is a chain of 2 carbons surrounded by hydrogens, and that propane is a similar chain with 3 carbons surrounded by hydrogen. That's a complete structural formula. Now there's a shortened version of this called the condensed structural formula. This still kind of gives you the order of the chain, but it does it in chunks, and it doesn't show you where all the bonds are. So ethane is, each one of these carbons has 3 hydrogens. So we got one carbon with 3 hydrogens, we got another one with 3 hydrogens. So you could just write it that way. You could write CH3, CH3. Or for propane, we've got a carbon with 3 hydrogens, a carbon with 2 hydrogens, and then a carbon at the end with 3. So we say CH3, CH2, CH3. Same. Now, if this all seems very complicated, hey, there's a way to make it even simpler. You can just draw lines. These are called skeletal formulas. Right here, this little line right here, that's the skeletal formula for ethane. You're expected to know that the points at either end of this line segment represent the 2 carbons of the chain, and you're just expected to know that each carbon is surrounded by hydrogens. Or here with propane, 1, 2, 3 points represent the carbons in that chain. Here are the next 7 skeletal structures for the various alkanes, and you can just count them for yourself. Butane, 1, 2, 3, 4. And again, the points in the jagged line represent the carbons, and you're just expected to know that all the carbons are surrounded by hydrogens in the basic structure. So these various kinds of structures can be used to attach functional groups to the main chain. Here's 3 different ways of showing a particular functional group that's called an alcohol. An alcohol consists of a hydroxide group, which is an oxygen and a hydrogen together. And it's this oxygen and this hydrogen together is substituting for a hydrogen. So instead of having ethane, which would be 2 carbons completely surrounded by nothing but hydrogens, one of these hydrogens has been replaced with a hydroxide group, OH. So here we show that hydroxide group on the ball and stick model. Here we see it in the complete structural formula, and here we see a version of the skeletal formula 1, 2. What is a functional group? Well, they get their name from the fact that they actually affect the way the molecule behaves. They affect its function. We say that they are specific arrangements of atoms inside an organic compound which are capable of undergoing characteristic chemical reactions. What does that mean? It just means they behave a certain way because, they've got that property. If a molecule, a chain of carbons doesn't have one of those, it can't do those reactions. But if you add one of those things to the chain, you attach it on the outside, suddenly it can do that particular kind of reaction. The truth is that since these things are on the outside, they're typically more reactive. Things are more likely to bump into them and react with them. And so most organic chemistry is actually functional group chemistry. Now, if you look at the slide, you may recognize the cartoon drawing in the middle. It looks like a bundle of dynamite. We've seen this in cartoons, the red sticks, and there's a fuse. They light the fuse. It may go off. It may explode. But what is it that's actually exploding? Well, it's shown here in the structural formula. So here we have a ring. Instead of line segments representing individual carbons, we have a ring. This is a series of carbons that have been chained up, and then the chain has been bent into a circle. And like a snake eating its tail, it forms a ring. So we're going to start here. It's got a methyl group attached to it. CH3 is a methyl group. We're going to call this first point in the hexagon carbon number 1. And this is 2, and this is 3, 4, 5, and 6. So there's 6 carbons arranged in a chain. The first one has a methyl group. Now, the second, and the fourth, and the sixth all have something going on that's kind of interesting. They have an extra line on the inside. That means there's a double bond between 1 and 2, between 3 and 4, between 5 and 6. And at the end of that double bond, in each case, there is a nitrogen group, NO2. NO2, there are 3 of them. The nitrogen groups are not terribly stable. They've got 2 oxygens, and they can release a lot of energy if they fly off, kind of destructive. And so this is, in fact, dynamite. These 3 nitro groups are unstable. They'll release energy if their chemical bonds are broken. And so this molecule is its technical name. It's called 2,4,6-trinitrotoluene. Called trinitro because you've got 3 nitrogen groups at carbons 2, 4, and 6. And it's called toluene because whenever you have a ring like this connected to a methyl group, that's a toluene. And of course, dynamite is very explosive precisely because it has these 3 unstable things all on the outside If one goes, they all go, right? Now, again, here's the common functional groups, and you'll see this in the organic compounds guide. This figure shows you the basic outlines of those things. Now, here's an example of 6 different molecules, and these have all been derived from propane. Monkeys eat peanut butter, so if I have 3 carbons in the main chain, and I do, 1, 2, 3, 1, 2, 3, all of these have 3 carbons in the main chain. So these were all derived from propane. What we do is we add different functional groups to different carbons in the chain. In the process, we change the shape, and we also change the function of the molecule. And so we reflect that change in shape and function by giving it a different name. So this is propane, but someone has attached a methyl group to the second carbon. So instead of calling it just propane, we say 2-methylpropane. Got a different shape. Or here, our propane chain at the very end, the terminal hydrogen at the end has been replaced by a hydroxide, or as we sometimes call it, an alcohol group. This isn't propane anymore. This is a version of propane that instead of being nonpolar, this version will dissolve in water. Now, again, regular hydrocarbons like the oil slick on top of a wet asphalt in the street, we see that shiny rainbow shape. They're not mixing. We see the shiny rainbow shape because they are nonpolar. They won't dissolve in each other. But alcohol certainly will dissolve in water. Why? Because this functional group changes the way the carbon chain behaves. And so since it appears on the first carbon by convection, we say this is 1-propanol. Instead of propane, it's 1-propanol. Suppose instead of attaching an OH group, we double bond the last carbon with an oxygen, and we put a hydrogen on the other side. Well, this is a functional group called an aldehyde. So we say 1-propanal. Instead of 1-propanol, it's 1-propanal. Or we could replace that with an amine group. So instead of this being propane, we call it propylamine. Or in the middle of the chain, we could, instead of having the carbon being surrounded by hydrogens, it could share a double bond with an oxygen. If that happens, why it's no longer a regular hydrocarbon, it is a ketone. And so we use the suffix -one. We change propane into propanone. Last one, we add a carboxylic acid group. And so when we do that, the rule is you use the suffix oic acid, 2 words, oic acid. So propane becomes propanoic acid. And you can see how all of these have the same basic shape, except for the functional group that's been added, highlighted in orange. Now, we see how adding these functional groups changes the function. Again, ethane by itself will not dissolve in water. It's got a very low melting point. It's below the freezing point. And the boiling point is also below the freezing point of water. And ethane by itself is colorless. It is odorless, and it's a gas. I mean, it almost never happens on Earth that we get to negative 88.6 degrees Celsius. I mean, I won't tell you it never happens, but it doesn't happen too often. So almost all the time, ethane isn't a solid, ethane isn't a liquid. Ethane is almost always a colorless, odorless gas. But if we add the hydroxide here, replacing the hydrogen, we change it from ethane to ethanol. Well, we lower its, we raise its melting point. We raise it. Look what happens. Instead of the boiling point being below that of water, being below water's freezing point, it's now above the freezing point of water. In fact, it's 78.5 degrees Celsius. This is more than twice human body temperature. And since you got to get it that hot in order to boil, well, ethanol is not a gas. Ethanol is a liquid, and it is colorless. But, alcohol does have a characteristic odor. And so, this alcohol group changes the function of the straight chain ethane into something else. The molecules behave differently. So that's all the material that we've covered in any detail. And I gave similar examples on the screen. I'm just going to point out to you, all of you, that this information appears in great detail inside the PDF file I've sent you, the Naming Organic Compounds Guide. And what I would recommend is, if this is all new material, I would recommend go back and first watch the PowerPoint video that I've already made this week that introduces some of this material. And then before you try to do anything with functional groups, you should do the assignments I've already given you with hydrocarbons. You should only be attempting the functional groups if you've practiced doing the hydrocarbons and if you've gone through the organic compound guide. You don't have to do anything on that guide. You don't have to hand it in. You have to work on it. It's just a reference point for you. But there's just so much information in it that if you don't use it, well, you're not going to do well on the other assignments. You just have to use it as the saying goes, it's your guide to figure out how to do the other assignments.